At this time, I would like to introduce then Chuck Newell, who will be giving us a presentation, and he will introduce his co-PIs on the project. He will be presenting on project ER-201126, which was Decision Support System for Matrix Diffusion Modeling. Chuck?
Great. Thanks, Andrea. Chuck Newell here, GSI Environmental. And today we've got a slideshow that's in the format for some of these debriefings, but because it's a software tool, software product, it's a little bit different format. But we'll go through this and hopefully give you an idea of what this tool is all about, why it was developed, how it works, how the machinery inside works, and then how it can be used to answer questions about sites. I'm here with Dr. Shala Farhat, who is really the key programmer, coder of this particular tool, and we're actually going to share duties on the presentation tag team-wise. So, Shala, you want to start out with slide number 1? Mm-hmm.
Well, that's just the cover. So our project was the Decision Support System for the Matrix Diffusion Toolkit, and as Andrea mentioned, it's project ER-201126. And this is the final debrief for the project.
Mm-hmm. Great. And the next slide is our project team, and we've got a couple of people listed here from GSI Environmental. Again, Dr. Shala Farhat, she's really the lead programmer, author of this thing. We have the GSI team members who did various things like do some beta testing. Can they get through it? Can they run it and all this? Tom Sale is also on the call, one of our collaborators. Tom, you want to just give a short summary of the team there at Colorado State?
Yeah, so it's myself, Tom Sale, and Jennifer Wahlberg is here. Jennifer, this work was, or supporting this effort was a large part of her master's thesis, and she's finishing that up. And then also Dave Dandy and also a guy named Jack Martin all helped out on our end. So that's us.
And Dave Dandy, he's in which department? What's his background?
He's the department head in chemical engineering.
Okay, but really a mathematical whiz guy, and came up with some of the original formulations for the software for the algorithms. Is that right?
Correct.
Okay, great.
So the technical objectives of the project were to bring to market two extremely useful but little used Department of Defense matrix diffusion models. And so the idea was to develop a decision support system with planning level modules that, two planning level modules, the square root model and the Dandy Sale model, that could provide that contained an interactive help guide and a user's manual, and then to beta test the toolkit using sites from ESTCP and CERTIF if possible. And then the final objective was to finalize the toolkit and make it available as a free, easily downloadable software package.
And some of the backstory is using some of our conventional numerical models like ModFlow, MT3D, really don't capture this matrix diffusion process very well. They don't simulate it very well. Tom, you did some research on that, and what's the story on that?
Well, the problem with at least traditional numerical models is that the blocks in the model are so big that they don't capture diffusion processes, and it turns out diffusion processes are super important. So So we've really been missing it in much of our modeling. So this is all analytical solutions, and they provide continuous solutions in time and space, and there's great convenience in that.
So the advantage with the analytical models is they are simpler, and they can run in a spreadsheet type environment. You get these answers. Perhaps one of the limitations are you have to make these simplifying assumptions, and we'll get into that. But there's an on-off assumption that's real critical for this. But let's go to the next slide. The next three slides are about performance objectives, really talking about if you're doing a field program, what happened at this field program. For us, since we're developing a software tool, we have these milestones of, hey, let's develop this mock-up, let's do this the module. We have these two separate parts of the tool we'll talk about. One is called the square root model, SRM. The other is called this Dandy Sale model, and we'll talk about why that's named that in a bit. But we have these two different actual options for people to use, and this just talks about how we completed these separate milestones by coming up with the mock-ups and the interfaces and all that. Mm-hmm.
So we had in total 8 milestones, and so the 8th milestone is the project debrief, which is basically happening today. So I think we were pretty much on target. And
I think Andrea said this just got on the ESTCP website today. Is that right?
That's right.
Great. Okay, great. performance objectives. I think we didn't have any of these qualitative ones, so to speak. Let's go to the next slide.
So one of the objectives was to test, once we've developed the software, to test it on actual field sites to see how well it was able to reproduce actual field data. And so we tested it at 3 sites, an industrial site in Connecticut, a sand tank experiment, and then a former dry cleaner site in Florida. And selection of these sites was based on how well delineated the matrix diffusion zones were, how well defined the low permeability layers were, and if there was any historical plume information available with good hydrogeologic data. And the point was we wanted to have good data so we could compare our simulated data to actual site data. So if we didn't have good historical data, it was going to be kind of hard to see how well our model was reproducing actual data.
And then we did these comparisons in different ways. Some of them are, can we match the concentrations in monitoring wells that are being affected by matrix diffusion? In one case, we looked at the penetration of the contaminants into these clay layers. Could we match that shark fin? And we looked at that. And then there's this famous green tank study, and we said, can we match the mass flux coming out of that thing? So all those things were in there. The test design, in this we said that we developed this piece of software, and then we had these beta tester out there, great folks who spent time going through the tool, seeing is it understandable, where do we need to give the user some more help, how does the output look. But here's this whole list of folks who did this. Ron Fault at Clemson University had some grad students work on it. Tom, you had your folks there tested, is that correct?
Yes, yep.
So did some of that. Hunter Anderson helped out, and then we had 2 folks from the Corps of Engineers who were very helpful, did a very detailed review of that. So let's go into the tools in the next slide, and let's talk about the first of these 2 modules. And this, we call this the square root module.
So basically, there are 2 main modules, but we also had a third module that we'll talk about in just a few minutes. But the first module is the square root module, and basically what it does is it estimates the mass discharge diffusing out of the low K zone, and low K means low permeability zone. It also estimates concentrations remaining in the high permeability unit, and also estimates the mass remaining in the high K unit. And then it also does uncertainty analysis, a Monte Carlo type analysis on certain parameters to see how they affect the result of the modeling.
Yeah. And one thing, just in terms of nomenclature, we're calling these silts or clay layers, or could be bedrock, but we call them low K units. And Tom, this is some nomenclature you're trying to have people use. What's the background on that?
Well, I think it's important that we all have terminology that everybody's recognizing, and it's a significant shift in thinking that we have zones that are effectively moving water and zones that are effectively not moving water, and the zones where the water isn't moving very fast, diffusion becomes super important. And so, yep, it's kind of a branding or a labeling thing. I think we should use the term low K zone.
Okay. And so this first model is the easy one. You can do it on your calculator, but it leaves some of the picture out there dark. You really can't, in this particular model here, you can't look under the hood. You can't look in that low K zone and see what that distribution of contaminant is. The second module here is what we call the Dandy Sail model. It does. It has much more sophisticated, the mathematics, a lot more complicated, but then you can go in there and look at the aqueous concentrations at any point in that clay that's been in contact with this matrix fusion process, total concentration, the mass, and it also tells you this transmissive zone. So Tom, any more you want to add to this? Why is it called the Dandy Sail model?
Dave, I proposed this idea in a 2003 AFSI proposal that we subsequently funded, and then Dave Dandy did the analytical solutions, and it is really complicated. It gets into Laplace transforms and stuff that most of us don't do on a regular basis. So Dave Dandy did all that work with great glee and joy, and now we've been working on using it and applying it, and it's really cool that this whole toolkit now makes this model available, because it was really difficult for anyone practically to run. So, but Dave Dandy is really the one who did the math, and it was my idea.
Great. Okay, so the square root model, think about that as the real simple guy. You can almost do it on a calculator. and you get in and out real quick. You can do this Monte Carlo stuff. The Andy Sale model is for matrix diffusion, more complicated, more powerful. And then we've got some Christmas tree ornaments hanging on there too, some extra stuff. And what's that involved?
Right, and so we called it a related tools module, and basically it provides summaries and a simple tool, a NAPL dissolution calculator, which estimates the transverse diffusion of contaminants that are passing over the top of a NAPL pool, and also the transverse diffusion of the contaminants into the locate zone unit underlying that pool. And then this module also provides some summaries, such as a summary for the plume magnitude information. It provides a summary on locate zone remediation alternatives, and also a summary on the 14K compartment model.
So one of the great things about working on these ESTCP projects is you get to throw in other stuff you've done. And so Shaul and I worked on this paper called the plume magnitude classification system, which breaks all plumes up into one of 10 categories. The Mag 1 plume is a real small one, a Mag 10 is a big one. And it tells you what magnitude plume is coming off of this matrix diffusion source that you simulate. And then, Tom, you did the 14 compartment model, right? And we've got that included in information in this one to tell people how you can use the toolkit to answer some questions in the 14 compartment model.
Yeah, you had something to do with the 14 compartment model too, Chuck.
Well, that's right. I remember, yeah, you and I we worked on it together. But really, your thing, you're the originator of it. That came out of the decision guide project, right, that came up with a FAQ document and then the decision guide. So that's another inspiration from ESTCP, I guess. So now let's go into look under the hood a little bit of some of these different models. And the first one is a square root model. And of course, in science, we all are standing on the shoulders of giants, and we're starting out with Fick's law. And here's this guy thinking about diffusion, that things are going to go from areas of high concentration to low concentration, and then it goes up through, I think, some work done by this guy Crank. And then 1994, Beth Parker writes a paper with some of these different diffusion equations going into from vertical fractures filled with DNAPL into these clays on the side. And then Tom, I think this is 2006, you guys write this AFC source zone initiative, and what's in that report? Let's see, Tom, still there?
Sorry, I forgot to unmute.
Okay.
The AFC report really got into the idea that there's transmissive and low K zones, and began to explore the implications of these low K zones in terms of persistence of contaminants in transmissive zones. And we did a whole bunch of really cool tank studies, and then we started working on models. And Chuck, you picked them up here, which was really cool.
So we took some of that, and you guys had these formulas out there. And the key thing is it's an analytical model, so they're these simplifying assumptions, and it assumes that there is a loading period. And if you look at that panel on the top right there, it says that if you released, for example, a pool of DNAPL in 1965, and it's there until the year 2000, then that's the loading time it goes into these clay, and you see these arrows. Then in 2000, on a Friday at 8 o'clock at night, you assume it's all gone and that transmissive zone's completely clean. And then as a simplifying assumption, the stuff comes back. We call this the release period. So putting in these 3 times is important, and that's when the release started, when this release when this loading period ended, and when the release period from the clay is occurring. You have to put those different times in there to make it all work. I want to note this can be a DNAPL source was the original formulation, but you can also have it as this is a plume of a certain concentration that is passing over this clay and then loading it. So it can be this NAPL source where the red is on top, or it could be actually a dissolved phase plume.
So as Chuck and Tom mentioned, this is a very simple equation. So as you can see, you can easily do this equation at the back of on the back of a cocktail napkin or something. And we call it the square root model because of the square roots in the equation. It's a very simple equation, and what it does is calculates mass discharge based on some very simple parameters such as the porosity, the loading concentration, the length of the NAPL pool, the retardation factor, and the effective diffusion coefficient, and the time when the loading starts and the time when the loading is removed. So a very simple equation and very powerful equation.
And one thing I did notice, it's a lot easier to do square roots in your head if you have a couple of cocktails in you, to do this calculation. But that's why I call it the square root model. They have some things that are new to people, though. The effective diffusion coefficient, something a little new, as opposed to when you're thinking about BioChlor, RemChlor, one of these models. Tom, what's the background on effective diffusion coefficients, and how are they different than regular diffusion coefficients?
Well, you can measure diffusion coefficients in a pure phase liquid, and you can measure how fast stuff moves just due to concentration gradients, and that's straightforward. But then if you add porous media into that, it blocks some of that transport, and then the porous media also introduces tortuosity. So you have to take a pure phase diffusion coefficient, and then you have to correct it for the cross-sectional area of transport, and then also the tortuosity of the flow paths. So,
okay. Interface helps you with that, right? Don't we give guidance on what tortuosity to use for different media and all that?
And we'll get into that, yeah.
Okay, and we've got some slides on that. Okay.
Yeah.
So that's it, just the square root model. Let's go to the Dandy-Sale model, and this is the more complicated one. This is from the Journal of Contaminant Hydrology paper, and it has a different source configuration. Instead of this horizontal plane that's lying on top of the clay, Tom, you assume a vertical plane, that piece of orange in there, and you want to describe the source configuration and what's involved?
Yeah, there's a source term, and this was what Dave Dandy did, and there's some fixed concentration right at the contact on the upstream edge there, that orange plane, and then that source constant decays or decreases vertically as you go upward. And actually, Dave Dandy and I figured that out because that decay of the source concentration above the contact looks a lot like a DNAPL pool. So in this paper, we say, well, this plane source right at the upgradient edge is analogous to a DNAPL pool, but we didn't really explain that or take it all the way. So actually, in this toolkit, you guys do that transform and actually turn it into an analog pool immediately upgradient.
And then just some other notes is the square root model is very simple. It assumes that after that certain time period, the transmissive zone doesn't have any contamination in it, so this diffusion is coming out maybe faster than it should. But your model, Dandy-Sale model, accounts for the concentration in the transmissive zone. Is that right?
Yep. Yes.
Okay. So it's a little more accurate, a little more realistic, I think. But
yeah.
You pay a price for doing that, and let's go to the next slide. And Shala, what's all this about?
Well, this, compared to the square root model, this is one of the equations that's involved in the Dandy-Sale model. And as you can see, it's a lot more involved. If anyone can solve this in the back of like an envelope, I'd really like to meet you.
It's a lot more cocktails.
Yeah, exactly. So as you can see, basically the objective of this slide was to show that it's a lot more complicated, it's a lot more complex, it requires a little more input data than the square root model.
And then one of the things we struggled with, there are certain zones where this model, at some point, it starts to blow up. And so we had to really be careful of that in coding this to make sure that problem wouldn't be transferred down to the users. And we think we found some good ways to do it. And Tom, any comments about that piece of the work we did? We had a lot of talks about that, conference calls, I know, to work around that issue.
Yeah, there's some of these arguments like e to the minus x, where x is positioned. It blows up when x gets super big. And we spent a lot of our time, and Jennifer spent a remarkable amount of effort trying to expand this solution. In the end, it's amazing. We've kept working on this, and we've actually now been able to overcome that limitation, which is exciting. But it's even more complicated. It's dramatically more complicated than this. So there's an opportunity for a second generation of this whole thing if people are interested.
And then just hundreds of hours of work on Jennifer's part and Shala's part, trying to get this knowledge in here in terms of these equations into the spreadsheet. Okay, so that's a little bit about theory about these two main tools. Let's go now and see what does this thing really look like. And so on this screen right here, we're going back to the square root model. Here's this data input screen, and this is what you got to fill in if you want to use it. And we break it up into these different categories, these 7 different categories. It's got what units are you going to be metric or English, hydrogeology, transport, plume characteristics, general characteristics, and then field data if you want to compare your information against. And so this is what this thing looks like. You can click on these different help buttons and get information. There are pull-down menus that you can use to, say, pick if your low K units of sand, a clay, or a silt or clay. or some sort of sandstone, some sort of consolidated material. So it's all in here, interactive help, and that's how this configuration looks right in here.
And one thing also is that any cell that's colored blue is a default value that the toolkit provides. So for parameters such as the porosity or the tortuosity factor, the toolkit or the diffusion coefficient, the toolkit provides a default value that the user can either use as a starting point or override if they have site-specific information available.
If you don't like it, you can get rid of it, put your own number in there. Mm-hmm.
So as Chuck mentioned, there's a interactive help guide and a pretty comprehensive user's manual that goes with the model. And so the model provides guidance on such parameter selection, such as which model to use, how to calculate these loading concentrations, which model area to select, and then which area to model and how to select that model area. And also suggests a way to calibrate which parameters to vary to improve your calibration. And the toolkit also provides default parameter values, such as for the porosity for both zones, the low K and the transmissive zone. It provides molecular diffusion coefficients for 13 constituents right now, the tortuosity factor for both zones, the organic partitioning coefficient for 13 constituents, and also provides equations for the vertical hydrodynamic dispersivity and the loading concentrations. So the user can override these if they have site-specific information, or they can use these as starting values and use them as calibration parameters.
Great. Okay, let's look at 4 slides of the output. And here's some of the things you can look at. Once you set the model up and say I've got a certain area that has been charged up with these contaminants into the matrix, into these clays or silts, for example, and it's been there loaded up for a certain number of years and it's been released. And now what we're seeing here are these graphs of some sort of metric versus time. The x-axis is time here. You control the horizontal, you control the vertical. You can see it over the next 5 years or the next 500 years if you wanted to. But the ones we've got in here, mass discharge, that's grams per day coming off of that source zone, which is a certain length and certain width. You can also look at concentration in the transmissive zone. We take that mass discharge, assume a 10-foot well screen, right? Mm-hmm. And we say that mass discharge is in contact with that well. You're going to get a certain number of milligrams per liter of your constituent out there at any time. And also see just the kilograms in the low K zone. And we have got 3 lines in here for all 3 of these. It's both what the most likely number is, but we also put in uncertainty bars. And right now they're fairly simple. They're a factor of 2, but people can put in what they think it is, a factor of 10. And so people can put these different numbers in there and see what they are.
So in addition to the graphical outputs, the toolkit also provides, the square root model also provides in tabular format on the top of the output screen, the time the simulated values were calculated, the mass discharge at each of those times, the mass, the concentrations, and the plume magnitude. So all this information is available on screen, so if the user is interested in that, so they can just look at the table.
And this next slide really talks about the uncertainty in there. We did want to put some idea in there. It's pretty subjective at this point. Is the default a factor of plus or minus 10, or do people pick that as one of their options, right?
They can pick that one as one of their options.
I think I say we think that our numbers are factor of 2, a factor of 10. But we wanted to tell people that this is what it looks like. So on this screen, we're actually seeing 3 lines here, most likely upper range and lower range. Then there are these squares, which says during this period of time there were actual measurements coming out of that well. And in this case, this is actually one of our case studies that matched pretty well. It was in the range that we had assigned for that.
So the second uncertainty option that the square root model has is a Monte Carlo analysis. And what it does is provides 4 different options, 4 different parameters that can be used for the Monte Carlo analysis: the loading concentration, the porosity, the apparent tortuosity factor exponent, and the retardation factor. And the user also has the option of using these 4 parameters or removing them from the analysis.
And so some of the output of this would look like this is mass discharge in grams per day on the y-axis. This is time. I think we're going out to
2005.
2005 here for these different things, and we're seeing a median, a 95th percentile, and 5th percentile of these Monte Carlo runs. How many different runs does it use?
It runs 1,000.
1,000. So you can put what your uncertainty is for these key parameters and see what the end output on this is. So this is what it looks like in the square root model. Just some other things to note. You can look at the output in terms of log or linear right in here in terms of the output, and you can print this out and throw it into your report. So that's a quick drive-through of the square root model. Now let's go to the Dandy Sail model. Let's look at the input for that.
And so the Dandy Sail model is set up very similar to the square root model. The input, again, is just one page. So you don't have to scroll through pages to enter data in. It's just one page. And like the square root model, you enter your system unit, your hydrogeologic information, your transport information, and source zone characteristics and general information. And once again, the blue cells are default values that the toolkit can provide if you don't have site-specific information. But because the Dandy Sail model is more complex, it requires some additional information than the square root model. For example, for the Dandy Sail model, you need to enter hydrogeologic data for both the transmissive zone as well as the locate zone. You need to enter the porosity, the tortuosity factor for both the locate and the transmissive zone. So it just requires a little more information.
So here's a question. How do somebody know which model to use, the square root or the Dandy Sail? Do we have a table in the manual that goes through all that?
There's a table in the manual and the interactive help guide that will help users figure out which model to use, what's the question they're trying to answer. Using that question can help them guide which model to use.
So if you want a sort of a very fast result, then you're only interested in concentrations in that transmissive zone, that square root model, the simple one, can work. If you really want to try to simulate the movement of these contaminants through these clays and you want to see that vertical distribution, you got to go to Dandy Sail. So let's go to the list of outputs here. And then, Tom, you want to do this slide in terms of the different outputs that we have that are in the Dandy Sail model?
Okay, so for the locate zone, you get this panel of the aqueous concentrations, and you also, both in 2D and then with distance. And also, and this is really important, you get the sorbed concentrations, and actually locate zones are pretty interesting. They often have large surface area, and they often have high fractions of organic carbon. So it wouldn't be unusual to think that the sorbed fraction might be a factor of 10 greater than the aqueous. So it's important to really be looking at not just the aqueous concentration, which we typically do, but also at the sorbed concentration. So that's really important. And then in the transmissive zone, you get aqueous concentrations, and I guess it's hard to see. Charlotte, maybe you can show where 0 is on this scale. Oh, okay, it's up there. So this is all the locate zone here. But you can also get concentrations in the transmissive zone, and you can get mass discharge across the contact, and you can get sorbed concentrations in the transmissive zone, and also total concentrations. And then you can also track aqueous sorbed and total mass in both the locate and transmissive zones. And this begins to kind of get to the premise of the 14-compartment model, which is all about tracking contaminants in all the different compartments that are relevant to our concerns.
And so this is a little hard to see, the actual graphic here. Sometimes when you first see it, a little hard to comprehend. But the x-axis is distance from the source, right, the x-axis. And then the y-axis is the penetration into the locate unit. And this just shows at any point, if you drilled a well and took a core, that's the concentration of TCE. And in this case, it looks like a shark fin, and that's because it had loaded up for a certain number of years, and that source had been removed or it cleaned up a lot, and stuff had started to diffuse out. So the shape of those curves are important to understand your site conceptual model.
One thing that's really important about this curve, so this picture of the locate zone is taken after the source has been removed, and you can see there's concentrations right at the contact near the top that are driving contaminants out of the locate zone into the transmissive zone, which is on top. But there's also concentration gradients below that are continuing to drive the contaminants into the locate zone, and that's really the insidious part of this problem, and it makes it hysteretic. In fact, contaminants go in much faster than they come out. And so that part of it, the contaminants, all the while that they're bleeding out, they continue to bleed back further in, is what really gives us these long tails.
And let's see that in real life. Let's now talk about the performance assessment.
So we applied it to 3 different sites. One was an industrial site in Connecticut, and we applied both the square root model and the Dandy Sail model. Then we also applied it to a sand tank study, and once again we applied both the 2 models. And then the last site that we studied was a former dry cleaner in Florida, and we applied the Dandy Sail model.
And so the middle site is actually this tank study that's done. It's not in the basement of the CSU lab. What is it called?
The garden level. Thank you.
Garden level, exactly. So
we work in the garden level. At least that's what we tell new students.
I like it, the garden level. Well, first we're going to go to Connecticut, which is close to the Garden State, I guess. And this is this classic research site, Chapman and Parker. It's an industrial site. They went out there. There was this metal manufacturing from starting 1952. They've got TCE and the sandy aquifer. It overlays the clay silt aquitard. And then 2000, they go out there and they see that there's this contamination that's in this aquitard below the plume. So here's this cone-shaped plume that's coming from this place. And the key point is they isolated this source here in 1994 by putting sheet pile around it. So we got to reduce this whole site to a couple of numbers, key numbers that are out there to throw into the square root model. And what are these key numbers?
So we had a lot of site-specific information available to run the square root model, such as the porosity, the Darcy velocity, the retardation factor, concentration, source dimensions, and when the source started and when the source was removed. The parameters that we did not have site-specific information, we used the Toolkit default parameters, such as for the molecular diffusion coefficient and the tortuosity factor. Now, if you notice here that we use an effective date for the source removal of 1996, whereas Chuck just said that the sheet pile was put in 1994. The reason we used 1996 was because it would take, based on the seepage velocity, it would take 2 years for a slug of clean water to make it to our observation well. So we used an effective source removal date of 1996.
So these are the numbers we threw in there, and then we basically ran. It didn't take very long to load them in there, right?
Nope.
And so it takes an hour, then you rerun it, and then this is what we got, and you're telling me you didn't adjust any of the values.
Nope. This is no adjustment of the Toolkit default values or the input values that we put in.
Okay, so maybe a little lucky on this one, but we've got the main line in the middle is the predicted value for this period of time, and we actually have numbers from one of the monitoring wells. And so this is the concentration in there. Now note this is a log scale on the y-axis, right? This is concentration in micrograms per liter. So these 2 bars on the top and the bottom are factor 10 higher and lower. But we are in that glide path, and it seemed to work pretty well. Okay. How about the mass and low K-zone? How did we do there?
So even the mass, where the Toolkit was able to reproduce the mass within an order of magnitude. So there was only one number that was published in that paper. So we compared that number to a Toolkit simulated number. It was within an order of magnitude.
Yeah, 3,000 kilograms,
right.
I think, is what they came up with, and in that clay, in that cone, and that's that square right there. Okay, we also went out and used the Dandy Sail model to look at some of the data developed by Chapman and Parker. And so here's some of their curves. And this is a curve actually looking in the clays. And this is in that source zone that's been isolated by the sheet pile. And the y-axis is the penetration depth into this silty clay aquitard. And then the x-axis is concentration. And we've got a bunch of the small points, the triangles and the squares. That's the actual sampling data they came up with. And then here are these 2 simulations we did. And some of this then depends on what loading concentration you use. And so why do we have 2 numbers here?
Well, for the initial run that we did, we used the solubility of TCE as the input, as the loading concentration, and that's 1,100 milligram per liter. And so that's the purple line. And then, we got a pretty good, decent calibration. But then we looked at the actual data, and the maximum observed data that they had was 1,300 milligram per liter. So we said, okay, if we put in 1,300, what's it going to do?
That's what they said.
Right. So the green line is using a loading concentration of 1,300. That's based on their the maximum observed concentration.
So that's actually in the source zone, and it looks like this because there's DNAPL that's still feeding the diffusion in there, and you have this exponential die-off as you go deeper and deeper in there. Let's go out at the edge of the plume, and this is after they've isolated that source, and you get these different curves here. Squares are their actual data, right?
Right, and then once again, in the x-axis, we're plotting the depth in the locate zone, and then on the that was on the y-axis, and then on the x-axis, we're plotting the TCE concentration in milligram per liter. And so, the orange line is using a starting concentration of 475 milligram per liter, and this was a source history. They had the step-down source history, so we used the average concentration as a starting concentration.
For the, well, actually, the loading concentration, right?
Right. And then we used the loading concentration as a calibration parameter in the year the source was removed, because we didn't really have a good indication of that. So the blue line is our calibrated line, and then the brown or red line is the initial run.
So a lot of scatter in the data, as you can see here, but the models is, and I think our goal here is really try to simulate the style of this thing, get a shark fin type shaped curve, and we were using this loading concentration as this calibration parameter, this knob to turn, and we think the blue gives a better fit, right?
Right, and it's a reasonable calibration.
Okay. Next, down to the garden level, Tom, you want to describe briefly about the famous green tank study?
Mm-hmm. So the tank study a woman named Leanne Donor did, and she took a 1 meter square sand tank, and she put clay and sand in it, and A, B, C, D are bentonite clay layers, and then she flooded it with fluorescein, and it was really cool because you could see the clay layers slowly turn green as diffusion drives stuff into it, and then she flushed it with clean water, and then you could see everything diffusing back out, and it's remarkable how many people have seen her video and the impact it's had. But anyways, you guys use this as a basis for testing the model.
Had to go in the tool and change a couple things in terms of some of the timing and things like this, but in the end, this is what we came up with. Mm-hmm.
So this is a comparison of concentration, fluorescein concentration versus the simulated concentration. So on the y-axis, we have the concentration in milligram per liter, and on the x-axis is the time. So this was I believe it was run for 128 days.
Yes.
And so the dark green line is the initial run that we did with just the input parameters, and then the light green line is the calibrated model that we have, and the parameter that we use for calibration is just the loading concentration. So I think we got a pretty reasonable match.
But one of the things is, if you didn't know what the result was, how close would we have gotten? And that's that dark green line. We're within a factor of about 5, I think, in there.
Right.
And then to get it to match, whatever reason, we had to really increase the loading concentration. And here's just, I guess the next one is just the observed versus simulated concentrations in there. And see, it depends on where we are. We get a closer match later out. But overall, pretty well done. This is the calibrated numbers.
Right.
Is that right?
And this is the Dandy Sail model.
Oh, that's right. We did the Dandy Sail model as well, and it matched a lot better, right?
It matched a lot better.
Yeah.
And the reason we picked this site was to see if, because the toolkit assumes 2 units, a silt and a transmissive zone, but this tank study and this case study had 4 silt units. So we wanted to see if we could model, if the toolkit could be used to model multiple silt layers. We
basically ran once and multiplied by 4
right.
to have the effect of all these different ones. Okay. Now let's go to Florida. Mm-hmm.
So this is a former a Navy site. This is a former dry cleaner at a Navy site in Florida, and Mike Singletary was the point of contact. And there was a PCE contamination, and for this site we had very limited site-specific information, so we used the toolkit default values as initial input values, and then we calibrated the observed PCE soil concentrations to see if we could reproduce those.
So this is actually work that University of Guelph and GSI did for another ESTCP project. We've got this vertical core. Let's use the Dandy Sail model and see how well it can simulate this curve in there. So again, y-axis is the depth into the low-K unit, the penetration depth. The x-axis is this concentration, effective soil concentration in milligram per kilogram of TCE. We first ran it was red. We get the red curve, and then we started adjusting, especially seepage velocity. It seemed that was an important one in the Dandy Sail model. And by turning these dials here, we're able to get a much closer match. And so it did say that having that field data, of course, in any modeling exercise, you get better information. But even without the uncalibrated one, still talked about or gave you this idea what that style of that response would have been.
So in a summary, the matrix diffusion toolkit was able to reproduce observed concentrations within an order of magnitude. So it provides a very valuable tool that can be used for optimizing site conceptual models, can be used for supporting site characterization efforts, for optimizing remedial design planning, for determining if matrix diffusion will affect remediation goals for groundwater sites, and can be used for the selection of more appropriate remedies that can effectively and efficiently address matrix diffusion. And so by addressing extended remediation timeframes that are caused by matrix diffusion, this can lead to savings in the project costs.
Okay. And Tom, anything you want to add about the overall key points of the thing? I think we got 5 slides after this, but go ahead. Mm-hmm.
Just one point, and that is the really cool thing about this toolkit is it captures the long tails that we're seeing at sites, that when we work on sources or even contain them or isolate or remove them, that we still have these long persistent contaminant tails, and we were kind of missing that in a lot of the models that we had been using earlier. They showed a rapid improvement in water quality down gradient that just hasn't been reflected in our field experience. So I think this is a real step forward because it looks a lot like what happens in the field.
So we're going to skip the next one, cost assessment, software project, but we did have some, there was a scale-up thing we want to talk about, and we did have some scale-up issues taking the standing sail model up into this bigger domains. And what's the limit, right?
Right now the limit is 1,500 meters, so that's about 4,900 feet. After that it kind of blows up, so we can't really use it. And also, it can be applied to fractured rock, but that has to be done manually. The manual does have a methodology, it does describe that, but the calculation has to be done manually. And
basically, you run it once, and then you multiply it by the number of
interfaces
you have, and you have to think about that in terms of this interface area.
Right.
And we have this section in there that helps people think about that. And we have default values for different types of consolidated rock in the interface, right?
Right.
For porosity and everything else.
Right. And also the toolkit does not, neither of those models account for degradation. So
right now.
Mm-hmm. So what we have done is we have proposed a new version, version 2 of the matrix diffusion toolkit. And with this version, we'll have no limit on the transmissive zone solution, so it will not blow up at any length. You can model a plume of any length. It will also include degradation and also sequential degradation, for example, the degradation of PCE down to ethene. It will also simulate the specific types of remediation processes, and it will also be able to simulate more complex source histories and conditions.
And some of this was built on while we were doing the matrix diffusion toolkit, but Tom, you guys have continued some of this work, and what's the latest on this, especially in the Dandy sail model in terms of capability?
So the good news is after a long and abusive treatment of a bunch of graduate students, we can do all that stuff. But we can do it in models that nobody's really going to be able to run, and they're really super complicated. So the cool thing is we've through persistence and some really nice work by the students here have been able to overcome most of the limitations that the current version has. There'll be a significant programming problem to get this into a format that people can readily do. But I was talking to Dave Dandy a couple days ago, Jennifer and I, and Dave assured us that we can do it all, particularly with Shala and GSI's help. So it's a doable thing, but there's a bit of work to it.
Okay. A couple lessons learned that we talked about, especially looking at some of our users fool around with it. They're not familiar with things like tortuosity and this effective molecular diffusion coefficient, so we beefed up some of the help there. Some of the computational issues, we've already talked about that, but that was certainly a lessons learned. It can be difficult down there if you've got 6 integrals all in one place. And then there was just a lot of global interest in it, and we've got people talking from Australia, Denmark about this thing. Available tools and training?
So, well, the biggest training guide is the user's guide, and that's going to be available at the GSI website and also at the ESTCP website. And we've also provided a short course. Chuck and I did a 4-hour short course at the 22nd annual NARPERM training course in November 2012, and we also hope to have a half-day training course in the 2014 Battelle Conference in Monterey.
And then last slide is we've done a lot of presentations about this, Denmark webinar, APA webinar, Navy, University Consortium, so a lot of different things we've done over time. And so the word's out there about the toolkit, and now it's going to be available for people to download. and that's what we have. So, so Andrew, at that point, that's all of our slides. We're definitely willing to take any questions or comments, I guess, at this point.
Great, thanks. Are there any questions? Well, I guess since there's no questions, Chuck, Shal, and Tom, I just wanted to take some time to thank you for providing this debrief. We find it very helpful.
Sounds great.
Yeah, okay.
We enjoyed doing it,
Must have
and
answered everybody's questions.
having the tool out there for people to use. And if anybody does get a chance to use it and they have any comments about it, things they like, things that they think could
need improvement.
Need improvement. We'd definitely always like to improve these things. Just sing out and let us hear it.
And our website always has a link, like, you can email we do provide like limited support, so that link is always available. So if somebody has a problem, they can always either directly email us or, from our website, they can send an email.
Yeah, we like talking about this stuff, so feel free to call us or email us.
One last thought on my part. Everybody here at Colorado State University really appreciates the financial support. It's great the students we've been able to support and to keep an idea moving. So thanks for the financial support.
Yep. Mm-hmm.
No problem. All right. With that, we conclude today's debrief. Thank you again.
Okay, thanks.